So that thing requires called density functional theory.
Yeah.
That is a computational tool you use to simulate materials. And I think 4 days generating some 25 graphs of the different properties of graphene and MOS2, and I simulated silicon.
Welcome to the After Hours Project podcast. My name is Vardhan. Today we have Amogh with us. Amogh loves physics and he loves research. And today he's going to come here and talk about that. He talks about his experience at an actual research center and what went down there, how he did his research there for like 2 months, what he learned there. And he also shares his, whatever insights he's picked up along the way. I met him because of his love for math memes. I love them too. But yeah, he just keeps sharing them on Instagram. And I was like, bro, come on, let's have a conversation. And here's how it went.
Amogh is a EE plus physics student. ECE plus physics student. My bad.
It's all the same.
Yeah. But yeah, someone the other day commented that they wanted more, like a podcast into research and things of that sort as well. So Amogh is going to talk about that. He's interested in theoretical physics, right? So complicated stuff. Amogh, break it down for us.
See, it's actually it's not complicated. See, the thing is, okay, I'll start with how I got interested in physics. It's a very small backstory. So one day, it's like this cliche story that I go to a planetarium and there I see all these stars and I get fascinated.
Yeah.
It's basically that cliche story which happened with me. Where I had a very nice high school physics teacher. And then it was all like it felt natural to me, taking physics in bits.
Yeah.
And then it came very naturally, like iske baad ye. It never felt forced on me कि मुझे physics करना है because
XYZ.
because XYZ, because this is cool. Of course it is cool, that's what I feel now.
Yeah.
But I didn't want to do physics because it was cool. It felt natural that ऐसा हुआ, and then I ended up here as a flow.
Yeah.
It's not okay. From an external perspective, it might be very intimidating and it might be very daunting. कि इतना ज़्यादा है, how can I even get started?
Yeah.
Well, that is true for any field if you think about it.
Fair.
Like Ishan was here a few episodes ago.
Yeah.
He talked about placements.
Yeah.
He talked about internships. Okay, if you want a corporate internship or if you want an IT internship, you have to start somewhere.
Yeah.
Because there is a lot of stuff to learn. Same thing in physics. If you want to get started, in like first of all, research. Well, it's a very boring job if you're not interested in it.
Yeah.
क्योंकि research, be it experimental or be it theoretical or be it research in general, be it in engineering, be it in any profession, research is where there are more setbacks in research than in most of the other fields, because you plan on something. Let's take you plan on doing a PhD. You get a time frame. Typically 5 years. 1.5 year, let's say, it goes away in getting your what is that called? Graduate entrance exams cleared.
Yeah.
And then you have typically 3.5 to 4 years to finish your research part of your PhD.
Yeah.
उसमें क्या होता है? You sit with your research advisor. You brainstorm for a problem which you and the research advisor feel is appropriate for your PhD.
Yeah.
And then you start working on it.
Yeah.
Sometimes what happens is, not sometimes actually, most of the times what happens is you start working on it, things feel fine for a while.
Yeah.
Say 3 months, 4 months, 5 months. You keep reading. That's your whole life. You go to some library, you borrow book after book and then you keep reading. फिर एक point आता है जहाँ पे you make no progress at all. I've heard stories where there are people in chemistry who are working on semiconductors. They collect a lot of data. फिर उसको analysis में submit करते हैं. And then what happens is they think, okay, yeah, this is what I've expected from the paper. This is what I've got. I will do the analysis, I will submit, I will write a thesis. What happens is, when they sit for the analysis, nothing goes as planned. So that is one of the major cautionary tales every person who wants to go into research is told. It's like, you want to do research, it is fine, it's a good thing, but you have to be aware of the risks before you dive into the ocean. Because if you want to make research as your career, once you dive in, there is little saving you from coming out.
Correct, yeah.
And I got I was telling you about this. I got a PS1. That's practice school 1. That's like a short 2-month, 7.5 something week internship at a research institution.
What is it called?
It's called Harish Chandra Research Institute. It's in Allahabad. Modern name is Prayagraj. It's in Uttar Pradesh. It was a very nice research experience. I got a very good mentor. I worked on when you're this early to research, it's a good and a bad thing simultaneously. Good because you demonstrate that you want to learn, that you have an appetite for curiosity. That is by far the most important thing you need to know. You need to have when you're signing up for research. The second thing is the thing why it is bad is because most research happens at a fairly high level. क्योंकि undergrad में जो हमें सिखा रहा है, I mean, the stuff is already figured out. मतलब there is nothing more to research on elementary levels. That already happened a long time ago. So that is a bad thing because there are a lot of prerequisites to know before you can work on your actual project. That is a universal statement for anybody who wants to get into research. Let's say in engineering, they'll give you like some 25 papers. They'll be like, read this in like 3 days, and then come. And then if you have any doubts, we can discuss in like 5 minutes. And then here's your project. And then these are the softwares you have to download. You download the software, and then you're like, ये क्या हो रहा है? What's going on? Because there are like so many buttons, so many. It's so intimidating at first. But like always, you need a good mentor. You need a good captain to sail this ship. This is not a very easy ocean to cross. Even the biggest of the biggest captains have failed. And they've had a lot of issues. I think I forgot the physicist. I don't know.
Just go on with the story.
So the thing was, he was a very very famous physicist, a Nobel winning. I don't know. I don't want to give out wrong information. It might be Max Born. I don't know. So PhDs back in the day when he was doing his PhD worked a bit differently than how it works now. So he had his graduate exams. He cleared that. Then he had they had 2 type of thesis or something similar to that. Like one was theoretical, one was experimental. This guy manages to clear the theoretical part of his PhD extremely well. Matlab top of his class, like that good. But then in his experimental part, he doesn't do that well. You can think of it like us getting C's. C is I think 5 or 6 out of 10.
I think 6 is C is a 6.
So he's at that level. It's very low. Matlab he was getting his PhD and then he just barely manages to graduate with a good enough credit in his name that he managed to get another job somewhere else. Later it turns out that this guy works on something, and then even later it turns out this guy wins the Nobel Prize. It's like that. So it's very very difficult for the uninitiated. If you have absolutely no idea, there's it's going to be very hard.
Yeah.
But it's a very slow process of building interest. Like building interest, it has to be a initially एक बहुत ज़्यादा interest होना चाहिए when you have to get into research. But then there'll be so many failures. There'll be so many down. Like it's like a slippery slope sometimes.
Yeah.
You fall so many times, and then you have to have that courage of getting up. You take up courses which you're interested in apart from the compulsory ones. You read other than what is required.
Yeah.
Than what is required. Matlab, what if it's just for exam purpose?
Yeah.
It will serve you a little good.
So are you reading anything? Are you taking other courses?
I have not.
You're dual-eyed. Do you have open courses that you can take?
I had space for 5 credits this semester.
What is that? Oh yeah, space for 5. Okay.
Space for 5 credits.
Yeah.
I took up my second course on relativity this time. So that's a course, general relativity and cosmology. That's one course I'm doing right now.
That's an elective.
That's an elective, correct. Apart from that, see, like I said, there are a lot of prerequisites to doing
Any research.
a fair quality research. Because unless you're crazy smart, without knowing a lot, you can't get much. You can't get through much.
Yeah.
So at least in physics, if you want to do research on the theoretical side, I'm not talking about experimental, because that's a whole different can of worms which I don't know much myself. So I don't want to comment on that. Theoretical physics, you have to be very good in maths. There is no such thing as I've done linear algebra.
Yeah.
मतलब यहाँ पे खत्म होता है. This is it.
Yeah.
Linear algebra सब देख लिया मैंने. That doesn't happen because you go down, it keeps pulling you in. It is that deep, and it is that interesting also, and that is used everywhere. You have the external observer will have no idea that linear algebra is used in what way. So
go back to your internship. Like, what did you do there? What is the experience like? What was the camp that you were doing, and what was the camp that they were doing? Like, what is the aim of that place?
That was a purely theoretical place. Like there were only two types of people. One were physicists, one were mathematicians.
Yeah.
That's all.
The
mathematicians, they were working in different areas like analysis, calculus, algebra, number theory.
Yeah.
I don't know much about that. Physics, there were people working in condensed matter. Condensed matter physics is something which deals with in a very loose sense of the word solids and how it behaves. There was high energy physics, nuclear and particle physics, stuff like that. There were people working in very cool topics like string theory and astrophysics, and there were a few people who were working on accelerator physics, like the one in Switzerland. Well, that guy actually collaborated with a guy in LHC in Switzerland. So it was a cool experience. I worked with someone. His name is Professor Sudeep Chakrabarti. He's a professor there. They call it reader. It is, I think, equivalent to assistant professor. I'm not really sure.
Got it.
He works on condensed matter physics. He works on structures of solids and how to use different solids in different applications. For that, I had to read a lot of background knowledge on a particular topic in physics called density functional theory.
What is that?
So that is, that is something which you use in simulations. You can't just keep building different materials क्योंकि तुम्हें explore करना है. Because it's not feasible all the time, it's expensive, time consuming, material might not be available, or it's not safe to build those type of materials. Yeah. So what you do is you simulate.
Yeah.
Best option, best alternative you have. Yeah. Computer है वो काम कर लेगा. So that thing requires something called density functional theory.
Yeah.
That is a computational tool you use to simulate materials. Generally. So I had to learn the maths and physics behind that.
Right.
That was a 7-week internship, 7.5-ish week internship. I spent the better portion of 4 weeks just learning the theory.
Yeah.
And then 1 week I had to spend convincing my professor ki, I've learnt it. Yeah. I know the very basics of how it works.
Yeah.
Please give something. Yeah. I want to work on something. That is how it works in research. They have to get convinced that you know your stuff. Only then they will have enough confidence in you to give you a project.
Yeah.
The simulation side was me downloading a software called Quantum Espresso.
Yeah.
That is an open source simulation package based on density functional theory. I was given the task of simulating graphene and different types of graphene, like you remove one atom of carbon and you put an atom of boron in it, and then see what properties change.
Yeah.
You remove that boron, put nitrogen, see what properties change. Similarly, there is another substance called MOS2, molybdenum disulfide.
What is that?
That is another two-dimensional substance like graphene.
Yeah.
And you use the same techniques to simulate that. See, the thing about that research internship, it was a very nice learning period for me.
Yeah.
Apart from this, it will give you the taste into how research happens, because that is a it's like that is a simulational job you have to do.
Yeah.
So it's like you have an idea, you write an input file saying I want these properties simulated and these are the properties of the solid I'm giving you, and then give it to me back. The thing is, it takes a long time to simulate. If you have, like, I simulated 18 atoms of carbon in a lattice. It's not much actually. 18 atoms is, well, you can barely see 18 atoms on a microscope, on a scanning microscope. But the thing is, you cannot simulate. I mean, you cannot simulate it at scale on your laptop, because I put once 18 atoms. I was thinking, okay, it's just 18 atoms. How long can it take? It took me 12 hours to simulate just one property of that.
Wow, crazy.
12 hours on one property. So when you get to that level, making errors is expensive.
Yeah.
Not in terms of money, but in terms of time.
Yeah.
You lose. This actually happened with me multiple times.
Tell.
So it's like when you give the input file to Quantum Espresso, you have to specify different properties of the substance, and then you have to mention the coordinates in 3 dimension where the atom is present, and then you have to tell which atom it is. Like, for example, if carbon is sitting, you have to say C, and then you have to specify the 3 coordinates X, Y, and Z.
Yeah.
So 18 atoms. So I was copy pasting one coordinate from one input file to another. I didn't see. The thing is, the C in the input file for carbon, it has to be capitalized.
Oh.
Yeah, I didn't. It is case sensitive. I didn't know that. Okay, and then to save time, luckily I was given access to their computing cluster.
Yeah.
So I had to do something called batch processing. I have to give multiple input files at once.
Yeah.
wait for all of them to come out simultaneously.
Yeah.
And then it happens sequentially, one after the other, and then the calculation at say step 4 depends on the calculations done in step 2 and 3.
Yeah.
And then that depends internally on calculations done in step 1.
Yeah.
If one fails, it's like a domino effect. Everything else fails.
Yeah.
And you don't know that initially. It will take the same amount of time for the error file to come out as the good file to come out.
Yeah.
What happened was multiple times. This happened to me at least three to 4 times before I realized what is happening. This pesky small lowercase c, it crashed my whole input file.
Yeah.
For the first one, effectively everything else crashed.
Yeah, and then you look at it and it's nothing. No.
And then no output is coming. It's just error. And then I'm not able to figure out what is happening.
Yeah.
And then it takes a lot of time and patience and not giving up attitude to even do. It takes that
tenacity.
It takes a lot of patience to say, okay, this is fine, this happens. And luckily, if you have good mentors, what they tell you is that this is not something new, even we face this. Just show me your input file. First, they will tell you, figure it out on your own. That's actually a good thing in retrospect, because it will give you the debugging skill. That is actually a very good thing that my mentor did, which I think of as which I think from hindsight. But sometimes just to save time, they just tell you, okay, this is the error you've made, fix it, and then it will work. And then it actually works. And then I spent I think 4 days generating some 25 graphs of the different properties of graphene and MOS2, and I simulated silicon. It's a crystalline silicon, and it was pretty cool because at the stage where I went, it was right after my second year, and I'd just done my elementary course in quantum mechanics 1. It was actually pretty cool to see the very basic fundamentals which I learned in class, and then you read a little bit more on your own, and then you get to do all these cool applications. You get to write code on your own. You simulate, and then I remember I'd made a simulation of ammonia. There's this cool thing where you know how in organic chemistry there are different projections. So ammonia it's like a tetrahedral structure. So what happens? It's like this, this, and this. It's basically like the Great Pyramid. One atom at every end. So ammonia does this very cool thing where 3 hydrogens, not Great Pyramid actually, it has 5 corners. It's like a triangular prism. I think Great Pyramid is a square prism.
Square prism, probably. That probably makes sense to me. Anyways, it's a triangular pyramid.
It's a triangular pyramid, and 3 atoms of hydrogen are here, and then nitrogen is on top. And then ammonia does this cool thing where it can oscillate. The nitrogen it can either be here or it can be here, attached to the hydrogens. And both of these structures are stable. And then ammonia keeps oscillating between them, and then the rate depends on how the temperature, how much energy the molecule has. If the temperature is high, if the molecules have a lot of energy, they rapidly switch between these 2 structures. I think it is a couple billion times a second.
Wow, crazy.
It's crazy. And then if the temperature is not that high, if it's not like room temperature, if it's like, say, I don't know, 50 Kelvin or something, the rate is pretty slow. And then I actually did this simulation. The input file gave me a list of coordinates. And then there is another actually cool software where you feed these coordinates in, and then it will show you the animation.
Wow, really?
Yeah.
Crazy.
That is pretty awesome. And then I showed this to my mentor. And then he's like, see, now you're enjoying this. So that was pretty cool. You suffer, and then and then something cool
Some
comes.
small success.
Some small success, and that is, I think, what carried my whole. That carried me writing the whole report actually.
Yeah.
Because all of this is fine. You have to write the report at the end,
Correct.
saying what you have done there.
Yeah.
And then I was pretty worn out at the end. And then this small, stupid little animation I'd done with Ammonia. And then I remember doing it with water also, H2O molecule.
Yeah.
These two animations, I basically, it was like a child who had done something very small. Like those people, they keep doing, I don't know, they simulate 5,000 atoms, they get all cool results, they publish papers in high-level journals.
Yeah.
Here is me doing some stupid little animation with Ammonia, it's oscillating. It's like a small child doing something great, and then the child is running around everywhere. I sent that file, that animation file, to literally everybody I could think of. I have done this. See, this is me. So that was pretty cool. And
That's
then
very cool.
that is very cool.
Yeah. So do you write all this code yourself? Yeah, so I talked to Mudit right now. He said like they use some, people have started using AI.
No.
Is AI good enough to write this, or how do you do it? Like, what is the code like?
No. This code, this software is
It's open source.
It's open source.
No, I'm saying the input file.
Input file, you write it yourself.
Yeah.
But ChatGPT, I tried using ChatGPT when I got stuck sometimes.
Yeah.
But it sucks. I mean, that is fair given
Depends
that.
on the training data.
Yeah.
Depends on how much knowledge it has about that anyway. So I'm not sure how much it will have because very niche field, right?
It's a very niche field.
Yeah.
I was the output file, it will give you the error, and then it will give you the error message, error number.
Yeah.
So the standard thing is you Google that error.
Yeah.
And then I used to get these. It's like one search result. All of Google, one result.
Yeah.
Saying this matches your search query. I click that, and then it's a copy of a transaction. Like say I am an Italian physicist.
Yeah.
You are an Italian. You are a Spanish physicist. I write this code, it's not working.
Yeah.
I send this code to you. You figure it out. You say, hey, that is wrong. This has to change. And then you send that email. You send that correction as an email to me.
Wow.
And then that email is posted on that forum.
What, really?
Yeah.
Wow, that's insane.
Yeah. So it's like one email, one search result.
Very, very niche.
Yeah, it's very niche. So like unless you have good people helping you, good the professor I used to work with, he was a very busy man. I used to meet with him hardly once a week.
Yeah.
His postdoc, he used to help me a lot. He was another thing about research in theoretical physics is that your PhD is fine. That's the bare minimum if you think about it. Actually, if you have to get a PhD, if you have to get an assistant professorship, a PhD in a good college, good university is the bare minimum.
Yeah.
After that, you have to do something called a postdoc.
Yeah.
It is the research you do after you get your doctorate.
Yeah.
And the guy who was helping me was doing his second postdoc.
Second postdoc.
Yeah.
Oh, so he's like done a PhD, one postdoc. And then
He was an assistant professor for a while.
Wow.
In some college.
Yeah.
And then he was doing his second postdoc. I think he's still doing his second postdoc right now. So
it's very, very difficult.
it is time consuming. It's like you know how the society makes jokes of doctors.
Yeah.
Saying, "Arey haan, doctor, you write NEET, you study till when you're 35 years old."
Yeah.
Well, research in physics, if you want to get a postdoc, you will be 30, 32, 33.
Yeah.
It's pretty similar actually. So
I mean, you have what I understand is the threshold is very high for you to contribute anything.
right.
So you have to get to that threshold first, because once you understand what the current landscape is, then you can contribute.
Exactly.
Right.
You need to know what is happening right now. You need to know the present to contribute in the present.
Correct. Yeah.
You need to know a lot about the past also to even have some hope of predicting the future.
Yeah.
So in that sense, AI was pretty useless.
Yeah.
ChatGPT was useless.
Yeah.
You don't write these codes on your own.
Yeah.
Like the software which I told you to make the animation.
Yeah.
It's called XCrisden.
Yeah.
I think it's because X for something.
Yeah.
Crystal density simulation, something like that. I'm not pretty sure what the expansion of that is.
Yeah.
But those softwares, unless you have a team of software engineers and computer scientists and physicists in that team, you cannot write that software or write that code on your own.
Yeah.
For example, Quantum Espresso, like I told you, it'll take 12 hours to simulate a basic graphene lattice.
Yeah, one property of that.
No, not one property, like multiple properties, like 5-6 properties.
Yeah.
Like density of states, that is one property. Band structure is another property. And you know how like there are multiple orbitals, sp. The density of states contributed by different orbitals can also be plotted.
Damn.
And then
Lot of stuff.
you can also plot how the 2D substance will look when you scan it in a atomic force or a scanning tunneling microscope.
Damn.
The computer will simulate that for you, so that when you have, like, let's say you make graphene in the lab and then you put it in the microscope, you can say, this is the image the computer simulated.
Yeah.
This is the image I got from the lab.
Yeah.
And okay, these two images look very similar. So that means what I have made in the lab is actually graphene.
Yeah. Oh, damn. Yeah, that makes sense.
Yeah. So it's like a check.
Yeah.
And it works both ways.
Yeah.
Your lab is the ultimate truth.
Yeah.
Whatever you see in the experiments is the truth.
Correct. Yeah.
And you can go back to your code and then change a few parameters to closely model the real world as much as you can.
Yeah.
Because another interesting thing about that internship was there were other guys from ICERS. I made a good friend from ICER Kolkata.
Yeah.
He was a bit early to HRI compared to me.
Yeah.
So he was, I think there was a 1 or 2 week phase difference between us.
Yeah.
He was doing MOS2 a week or two before me.
Yeah.
And then there is this thing called a functional.
Yeah. You can have some.
Yeah.
Absolutely.
So there is this thing called a functional in Quantum Espresso.
Yeah.
So it's like if you want a fine enough result, it's like a hand wavy result. But that hand wavy result is also pretty good. It's not like you're off by 50%.
Yeah.
If your error tolerance is somewhere around 10 to 20%, you use something called a PB functional. Okay, that is so that your computer can simulate it pretty quickly.
Yeah.
And then it will spit out the result. But let's say you want your tolerance is not that high.
Yeah.
You want a very good result, say within 1% or within 0.5%. You use something called a hybrid functional. That one, hybrid functional, that is a very, very cheeky thing. It will take a very, very long time.
Yeah.
And I'm talking time scales of orders of weeks. 3 weeks, 4 weeks. On the cluster, I still remember someone, like your laptop, it has 8 cores at max, 16 cores in very good computers. Someone had requested, like they had put their job, like they submitted their job on the supercomputer. I and that guy, my friend, we used to request, the maximum we were allowed to request was 24 cores.
Yeah.
That was the cap we had been told. You cannot request more than 24. Someone there had requested 196 cores to simulate, I don't know what that is. It was a very complicated crystalline structure. And that job had been on the cluster for 4 weeks.
4 weeks.
And it
196.
was 196 cores, 4 weeks. And I was told it was halfway done.
Oh, shit.
You realize after 8 weeks, that is 2 months.
Yeah. Oh, your entire internship was that long?
That it was that long. Now you imagine that guy who submitted the job, usne capital mistake, he makes that mistake. 2 months of his postdoc is gone there.
Oh my goodness.
So now you see at what stake you're dealing with.
Yeah.
That is the level of you have to be very good at what you're doing.
Correct.
Because if not, then 2 months is nothing. In those types of ऐसे उठ जाता है.
हाँ, correct. Bro, that is insane.
It is insane.
Yeah.
But then if you do it well,
Yeah.
that 2-month simulation
Yeah.
that can easily be submitted to a very good quality journal.
Yeah.
And then that was what I was told actually. My professor, he had, I'll keep it here.
It's fine. Keep.
He had written a paper.
Yeah.
So a lot of people, this is another thing in research.
Yeah.
There is good quality research, and then there is great quality research, and then there is research. So and then there is something which it's called peer reviewed research.
Yeah.
So
that is the highest standard, right?
That is the highest standard.
Blind, double-blind study, whatever. That like, I say, what is it? No, double-blind is for medicine. Sorry. Yeah.
I'm
peer
not sure about that.
Yeah.
But in physics, peer review, like in general, peer review is like we both are experts in the field.
Yeah.
I come up with something new.
Yeah.
I simulate something. I do some research.
Yeah.
And then I say, hey, look at this.
Yeah.
I found something interesting. I want to publish.
Yeah.
But it may so happen that what I've done is wrong.
Yeah.
Because some bug, some error, it can always happen.
Yeah.
So what you do as my peer is I write a paper, I submit it to the journal, and then the journal editors, they will forward that paper to
a peer. Yeah.
Who is an expert in the field.
Yeah.
And that guy, that person goes and he reads the paper, and then they're like, "Oh, this is interesting. Can you share this with me? Can you share how you did your calculations with me?"
Yeah.
Or they might tell, "This is not accurate enough," or "You need a control for this," or "You need." They will have some critiques, some comments, and if you satisfy them. And if your peer is satisfied and you publish it again, that is a peer-reviewed journal. And like you said, that is the highest quality research that can happen. And publishing in a peer-reviewed journal is fairly difficult because first of all, you need to do good quality research. That is not easy. And then you need to have enough courage to withstand the critiques.
Correct. Yeah.
Because it might not always happen that your peer is nice to you.
Yeah.
They might be very critical, and sometimes this keeps happening. Your paper gets rejected.
Yeah.
They might cite a valid reason.
Yeah.
Or they might cite a not so valid reason, but you have to deal with it.
Yeah.
And you do this research, and then you submit it in the journal, and then it gets published. And then that is the end of that research.
Yeah.
But sometimes what can happen is that after it gets published, even you as my peer could not identify some mistake. A reader, an external person can identify the mistake, and then they can contact the authors and the journal saying, okay, I think that is wrong. That study is wrong. So what happens is that you redact.
Wow. Yeah. Correct.
And that is it's like one of the biggest insults.
Yeah. To redact a paper.
To redact or get your paper off.
Yeah.
Because it's like you did so much, but then
take back what you said.
Take back. It might be an honest mistake. It's not like there was foul play involved, but it's not very highly looked upon.
Yeah. Makes sense. So anyways, I don't know how we got here. Research, PhD, papers. Okay, so that thing took like 8 weeks to do. Actually, I'll tell you one interesting thing that I saw recently come up. You saw who won the Nobel Prize for Chemistry this year?
They were computational chemists. Same thing with physics actually.
Yeah.
They were computational guys.
Really?
Yeah. Oh. So it's like.
So no issues. So I think this time this person won, right? The team from AlphaFold. So I mean I sense similar patterns actually to you guys. The modeling of the things. So you know what that is? The AlphaFold. Basically, proteins go, if you arrange the 3D structure, if you put whatever protein ke base amino acids, I'm guessing, they form a 3D structure. And so simulate karna is difficult, apparently. And they figure out like a way to do it. And that has reduced the amount of time it takes to do the research on that. Right? I sense this is a similar pattern. Like, do you think similar, like, Is that similar to what is happening with yours?
It is similar.
Yeah.
Interestingly, you brought up the Nobel Prize, this year's 2024 Nobel Prize. A lot of people I was seeing on Reddit, LinkedIn, and on Facebook, Twitter.
Yeah.
People were mad, saying, "How can you give a computational physics person a Nobel Prize? How can you give computational chemists a Nobel Prize?" That is not actually why the Nobel Prize is given.
Yeah.
It's not like, acha, physics, so you have to be an astrophysicist, you have to be a particle physicist, or you have to be a condensed matter physicist.
Yeah.
Only then you'll get a Nobel Prize. It doesn't work that way. The way it works is, okay, there is a really difficult problem there,
Yeah.
and here is someone who used a very clever method to solve that problem.
Correct.
And that problem, it benefits all mankind.
Yeah.
Like this protein folding thing you brought up.
Yeah.
Like you said, it is very difficult.
Yeah.
Like there are 20 amino acids, everybody knows that. But how those 20 amino acids arrange in 3D to give you a structure, that is very important if you want to understand the biochemistry side of it, which I have absolutely no idea about. It is all popular science, which I keep seeing on YouTube.
Yeah.
So my understanding of that is zero.
Yeah.
So it is very important nonetheless.
Yeah.
So you need a way to simulate what happens, because you always can't do experiments, like I said. That is why you simulate. So in that sense, what I did was pretty similar to the things which happened. No, it was not similar in the sense that they used machine learning and artificial intelligence, but it was a computational project nonetheless.
No, I'm saying, like, if there are parallels, because it takes so long, it took long before also. Like, I'm thinking maybe something that I could look into later on. I mean, it's very physics heavy, but like, I just wanted to put it on my project directly, and this gives me like a good. No, it's fine. I was just checking. It gives me like a good thing to look into later on. But yeah, very, very interesting stuff, bro. Like, especially if it takes that long to run on things, there must be something very, very complicated going on in the background. All those calculations and like,
they're insane.
Yeah.
they're
What is it, like? What is happening at the base? Like, is it addition, subtraction? Is it integration? What is happening? Like,
at the hardware level, if you think about it, it's just addition. Your computer can't do. It's just logic, right?
Yeah.
You just flip bits.
Yeah.
That is at that's
because it's a competition.
That's the most elementary level. But in terms of physics, like I'll give you my example again. In density functional theory, what that theory says is that you have to figure out the ground state structure, ground state electronic structure of a particular substance.
Yeah.
Because like hydrogen atom is very simple. You can solve it completely. Pen and paper, you sit down, you know good maths.
Yeah.
You can solve the hydrogen atom completely. You can write it in terms of fancy functions, but there is a full stop at the end. It'll end.
Yeah.
The function will end. But if you even take H2O, for example, you cannot write down the complete structure in terms of a function.
Yeah.
Completely. There is no full stop there.
Yeah.
It is a ...
Oh.
Even as simple as water, even as simple as ammonia, it gets crazy complicated, crazy fast.
Yeah.
So what happens is the computer, it's very fancy actually, and it's very cool. So your computer says, okay, forget the actual state, I will approximate. That is a very physicist thing to do actually. If you don't know what's happening in real life, if you can't get the exact thing, approximate chalega.
G equal to 10.
G equal to 10, pi equal to 3, cow is a sphere. It is fine.
It's fine.
As long as it models your reality with the error which you are fine with, it is fine.
It's fine.
So your computer says, let me guess a solution, and then it will plug it into the equation. Ordinarily Schrodinger's equation. If it is not a very fancy structure, Schrodinger's equation. It will plug it in, and then it will check both sides, LHS and RHS. And then this is a very crude way of thinking about it. It will check how much difference it is. And then it will say, okay, this difference is more than what this guy wants.
Yeah.
So what I'll do is I will change it a little bit, change the initial input a little bit, and then I'll try again. And then the output comes, and then you compare again.
Yeah.
How much the error is.
Correct.
If the error is again more, you change it again a little bit.
Yeah.
And then you keep doing that. It's like an iterative process.
Got it.
You keep changing until you hit a point where the difference is less than the error you are okay with.
Correct.
And then at that point, your program is like, oh hey, let us stop here.
Good enough.
Because this is good enough for this guy's applications. And then we'll just give out the results. That is what happens.
Yeah.
That is the heart of
Simulation.
approximation.
Okay. Yeah.
You have to specify the error up front. In Quantum Espresso, if you don't, it will take the default value. I think it is, I'm not sure. It's 10 power minus 6, 10 power minus 7. I use 10 power minus 8.
For, what? 10 power minus 8 what?
10 power minus 8 is the difference I'm okay with between the actual value and with what the computer says.
What is the order of the right answer?
Order of the right answer should ideally be 0.
Okay. Yeah, but no. Okay, wait.
Because if like you can't get an actual answer, right?
Yeah.
Because it is like it's if you want to think about it even more generally, it's like Taylor expansion, right? You have e power x, but if you're e power x at x equal to 0, if you want to approximate, if you're not going that far away from x, it's very small.
Very small.
You can do with 1 plus x.
Yeah.
You can if you want even further, you can do 1 plus x square by 2.
Yeah.
And how much you want to use the Taylor series is up to you.
Correct.
That error is what you specify. And your program stops at that point where the where its error is less than the input error.
Got it.
And then
That's how the simulation ka approximation works.
yeah, that's how generally simulations happen. And then, like I told you, it's an iterative process. The computer, you also specify what initial guess you want to give. And depending on that, the time taken by the program is different. For example, you can just say start with a random function. That will take more time, but what I noticed was if you start with a random function, after the program terminates, you get a closer value of the actual results. Actual meaning the experimental results. Because like I said, your experiment is the absolute truth.
Yeah.
In science, your experiment says something, you repeat it multiple times, you get the same answer. That is it. That is the truth.
Yeah.
Your simulation has to match that.
Correct.
So if you're what was I saying?
So the experimental truth, ground truth. If you start with a random function.
If you start with a random function, sorry, I forgot.
That's okay, bro. Sometimes even I lose my train of thought.
Yeah, so if you start with a random function, and then it keeps tweaking, that takes more time.
Yeah.
But if you start with a very intelligent guess that smart people have figured out that this can be a starting point, that will take less time.
Directionally correct, you have to be like that.
So you have to follow. It's like a converging series. Sometimes it converges, sometimes it doesn't converge. You stop after 50 cycles, it gives you one answer. You stop after 55 cycles, it gives you another answer. That is another thing with simulations. It doesn't necessarily give you the answer.
Damn.
Even if you have all the resources in the world, the series may not converge at all.
Wait, so how do you even know if it's going to converge or not?
You find out.
You do and find out?
Yeah, you do and find out. No, there is no warning. You go there, you drown, and then you're like, okay, let's not go there. Yeah, it's like that. That is how it works.
That's how it is.
Yeah. And then that is how the experts learned.
Yeah.
They failed multiple times.
Yeah.
So they know where not to go.
Correct.
And then they will tell you that, okay, these are the possible drawbacks.
Yeah.
Figure it out. And then they will let you fail so that you know where not to go.
Correct.
And you know where not to make the mistakes.
Yeah.
So that was pretty nice. So simulation wise, sometimes it happens, sometimes I remember for water, I calculated the bond length of water. It is around 1 point something angstrom.
How close did you get it?
0.05%. Insanely close. That was another highlight of the internship there.
Yeah.
So that stupid little animation. Yeah, that was nice.
I mean, like you know that you're heading the right direction when you're getting things right.
Yeah.
You're like, acha, okay, whatever I'm doing, is at least in the right direction. I'm heading towards the correct thing.
It's a momentary boost in your confidence. It's like a sudden euphoric movement, sudden rush of adrenaline. Yes! 0.05% error when I was only asked 1%.
Oh damn.
Yeah.
No, 20 times less than. Oh my god. Crazy.
I mean, to get that much error, I had to modify the code, change, iterate multiple times, and then I got it. And then my friend, he gave up. Because he was working with, remember hybrid functionals, that thing which took 4 weeks. He was simulating, I think, 6 or 7 atoms of, I don't remember how many.
ISO friend?
Huh? ISO Kolkata. He was simulating using hybrid functionals, and then it didn't come out only. He submitted the job in the supercomputer. It was chilling there. It never came out. And then it was time for him to leave. And then he's like, you know what, I'll just delete the job so that someone else who's in the queue, their program gets submitted. Because this is not happening anywhere. So
he couldn't finish.
He couldn't finish. He had done MOS2 using normal functional, but using hybrid functional, he couldn't do it.
Oh, bro, I mean, you have to take that. Like, you have a fixed amount of time. That is also some sad.
So it's like fixed amount of resources actually. Fixed time, fixed money, fixed it's like fixed manpower also. How many people do you want to devote to this task?
Correct.
All that you have to see. And then the error also you have to be fine with. It's like, are you fine with this error for your study?
But don't the errors compound? Like, let's say 1% here, 2% there, 3% there. You have to be careful where you allocate how much error.
That is a skill actually. You learn it only through experience. You can't just say, this step, if there is not more than 5% error, we cannot proceed. Because you're working on a time constraint. So that is something which you learn eventually.
And so that was your experience with PS. Abhi uske baad, where do you want to go ahead? Like, abhi masters, PhD, I'm sure you're going to do all of that.
See, it's like the benefit of this degree I'm getting here. It's an integrated master's. So
any interesting? Sorry, I'll just continue with that. Just one quick thing. Any intersections of ECE plus physics that you want to explore?
A lot actually, but I'm not sure if I want to explore. But for someone who is interested in physics but doesn't want to do the theoretical side that much. Let's say their math skills are not that good. Because like I said, you need a lot of good maths under your belt to even understand what's happening. Because it is very intimidating. So in that sense, you can explore different fields in electronics, like not just electronics actually, electrical engineering, instrumentation engineering, even mechanical engineering. You can, like, because physics is a very, very broad area and engineering is also a very broad area, the overlap is something which is very interesting. So let's say you can work on fabricating semiconductors, exploring different materials for semiconductors. That was an actual that was a problem which my professor was actively working on. He was with, like, there were multiple postdocs under him. With one person, he was trying to figure out there is a catalyst, and then there is a promoter. How can you use a promoter and this catalyst in this particular chemical reaction so that the speed, efficiency, and all of the other things are optimal for this person's particular application, industrial application. So, and then energy storage, energy transmission. That is a very
all physics plus
electronics engineering. That is a very good area of research as of now, because energy is something which we have to figure out. Because
computation is getting more heavy.
Without energy, there is nothing. You cannot do pretty much anything. So
I saw this one thing where you could judge how good a society is going by the per capita energy consumption.
Exactly. Right? It actually goes much more than that. It's not just society. It's civilization. Even like there is a scale on which planetary civilizations are ranked. I again forget the name.
It's okay. 5 stages. Continue.
It's 5 stages, and then that is solely based on how much energy the civilization is consuming.
Damn.
Like a type 0 civilization is able to, a type 1 civilization is able to completely utilize the energy of its host planet.
Yeah.
A type 2 civilization is completely able to utilize the energy output of the host star.
Yeah.
And then type 3, it's host galaxy.
Oh my god, like that.
It's like that.
So we are not even type 1 yet.
We are not even type 1. The last I read somewhere was type 0.8, type 0.75, something like
Wow.
that. We're almost
We're getting there, yeah.
But if we get there, it's going to be pretty dystopian.
Yeah.
So,
We completely used all of it.
oh yeah. It's not completely used, using.
Oh, you have to have the capacity to use.
Capacity to use it.
Fine.
It's the judge of your appetite. So energy is something which you have to figure out.
Correct.
And then, like when I was applying for colleges when I was in 12th, I was very interested in aerodynamics and aerospace engineering.
Yeah.
But I was not accepted to any aerospace or aerodynamics type of programs.
Yeah.
So when I came here, first year I saw that mechanical people have this option of doing aerospace minor. And then I was very excited. I will take mechanical in my after I finished first year, and then I will take up this aerospace minor. Then I got C in thermo, and then I was like, nah,
This is not for me.
nah, this is not happening, because that was one topic which I was not able to wrap my head around.
Yeah.
And then
That's okay.
that was the end of that fascination.
Yeah.
But then luckily I was able to figure out very quickly that I'm still interested in physics.
Yeah.
So that is something which may not happen to everybody. That at a very young stage, at a very early stage, knowing what you want to do is not that easy. And I'm on the lucky side where I know that I'm very interested in physics, and I would really like if my career was in something physics something. I don't know what yet, but
something.
physics
Yeah.
something. So you have to be very lucky also to know that, okay, this is something you will like to
That
follow.
interests you.
Yeah.
Man, I mean, that is okay, fine. Come back to that. Where are you going ahead? Like, masters,
Masters.
PhD?
You
You have a bite first, then you talk about this. I've kept you hungry for long enough.
No, it's fine.
So, masters, PhD, क्या सीन है, क्या plan है? Where are you applying? Even for maybe thesis. Are you doing a thesis abroad or thesis in India?
Oh, that's fifth year. I've still not given it a thought. Like, I've given it a thought, but not that deeply.
Yeah.
Because, it's uncertain. Fifth year is 2 years from now.
Yeah.
Almost.
Correct.
I've spoken to a few good seniors.
Yeah.
Who have done good internships, good thesis internships.
Yeah.
And the thing is, you need, again, coming back to the question of how to get into research, this is something which you have to be very good at. Well, that thing is CGPA.
CGPA.
I don't know if Ishan mentioned about CGPA in his...
He did.
He did?
Yeah. But his was more placement focused. I think for research and all, you need like at least 9 or something like that.
At least 9 is for very good colleges, where it is like very good.
Yeah. Like
But
Berkeley and all.
But 8.5 is minimum.
8.5 is minimum.
That's what, like, I go to a professor, I'm like, sir, give project. They're like, tell CG.
Oh, yo, really?
Yeah.
Bro, I think, juniors, they get this wrong impression in the first year. Someone tells them that CG is not important.
Yeah.
And then
that is something which, wrong impression.
The rest of their college life, that first year ka CG always...
it always matters.
Yeah.
There's a big baggage you carry right from first year.
Correct.
So...
And it becomes very difficult to improve it. Because what differential grade karna is more difficult.
That is true.
Yeah.
It's very difficult.
First year if you get good, much
It is easy to maintain.
Yeah.
And it is easy to improve from there. But pulling it from
low to high.
Pulling it from the depths of hell to something which is decent.
Yeah,
it is very difficult.
Yeah.
Many of my friends and seniors, I keep seeing them struggle.
Yeah.
And it's difficult. It's honestly tough. So coming back to the question, fifth year is something again. I have given it some thought,
Yeah.
but I don't know yet.
Yeah.
But fifth year, as of now, I think I will do a 2-year, two sem thesis, the off-campus thesis.
Yeah.
That is my plan. That is my dream. But I'm not sure.
You have
how-
time to improve your CG, no, Abhi?
yeah, but that is still something which I have to figure out why I have to figure out the logistics,
Yeah.
finances, all of that.
Yeah.
And then after that, it's like in Europe, I've heard that with a good paper in a good journal, the chances of you getting into a good university will improve dramatically. Apart from all of your good recommendations, ACADS, CGPA, projects, all of that, a good paper is something which is not crucial, but it's like if it's there, it's very good.
Yeah.
And in the US, they judge more holistically.
Yeah.
Right from undergrad level, they're like so everything. So for the PhD, I am not sure. It's like it is a thing I want to do.
It's very far also.
It's very far away to think of it. It's like you're planning for almost 3 years from now, 4 years from now. So I don't know how it will happen. I don't know if my tomorrow's morning 8 a.m. class will happen. So
Yeah.
or if we will wake up for it. So thinking of, I mean, you have to give it a thought. You have to prepare yourself, your family mentally.
Correct, yeah.
But that is something which it's like I have thought about it. PhD, like I told, first year and a half, not much research happens actually. You get accepted to the school, and then they teach you. You study very high level topics in basic physics. Whatever you learn at an undergrad level, they go to the absolute limits of that. Make sure you understand all of that, because without that you can't pretty much do research at that level. And then you spend the better portion of 1.5 year preparing for your graduate entrance exams. They call it, I think, graduate qualifying exams or something.
Yeah.
And then after you luckily hopefully pass your graduate exams, you sit with your research advisor, you sit with your mentor, you sit with seniors, people who have done PhDs. And then there are, as far as I've heard, there are 2 types of PhDs. One where your research advisor is like, that problem, work, go. Second type of PhD is like, both of you sit together and then you are like, hey, you know what? I was looking at this paper and then they say that has not been done yet. And then that sounds very interesting. So I will do my project on that. And then even your research advisor probably has no idea on that. Because that paper might have been published a few days ago, a few months ago. Don't know. So that is very new. So that is very risky. And in the long term, what I've heard is that is better, because it's like a risk. If you take it and it works out well, then the research you did was very good, because that was an actually difficult unsolved problem which you and your research advisor sat together and solved it.
Correct.
And that is also very good, because at a early stage you are able to identify what are the problems we are facing in this field right now. But if you take the other PhD where research advisor says that problem, go, that is like it's like a hand down. It's like, okay, yeah, fine, this is what I've been told, I'll just do this. That is a safer option. I'm not saying one is better than the other or this is worse than that, but both of them have their pluses and minuses. And it takes a lot of mental strength to select the second type of PhD where you're like, I'm fine with however this happens, I'm fine with it, because if it doesn't work out, then it's as good as you're spending 3 years and you're chasing a ghost.
Yeah, and nothing comes.
And nothing comes out of it.
Yeah.
And then you cannot publish. So it's very difficult.
Yeah.
But if you go for the safer option, I don't know. You might graduate, but like I said, I'm not saying one is better than the other. But pluses and minuses, you weigh.
Risk and reward, there's a balance.
Yeah, you have to. Again, like with the error tolerance, you have to specify the error tolerance which you want with your life.
Yeah.
And if that is fine with you, you go with either one. And based on your, like after you qualify your graduate exams, you know where you are, where you belong.
Correct.
Because at that level, you're only with the smartest people. Like there is that famous saying which says, be the dumbest person in the room.
Yeah.
And that will help you improve. At that level, you're always the dumbest person in the room. When I went to HRI, like 3 of us from this campus went. Purposefully because we wanted to experience how research feels like. Every time my professor used to invite invite me for a talk, his peers or his postdocs were giving. I was like, yeah, they're speaking English, but I'm not understanding anything. It's like, I know that is carbon, that is something, that is a nice color, and that's a nice PPT, nice watch, by the way. I don't know what they're talking, because I was the dumbest person in the room. And when you're doing your PhD, it's always like that. You choose a program where you are the dumbest person in the room. That will help you improve. So, again, that is a very far off thing.
Don't know what it yet.
Something I know, but not a lot.
Correct.
Figuring it out on the way.
Yeah. Man, okay, we have around 13-14 minutes because I have a meeting with my prof. So, quickly, I know there's a lot more that I wanted to discuss actually. I don't know how all this time passed actually. I have zero clue. But yeah.
No idea.
I wonder, like, what the way we got to talking was, I saw the photos of moon that you clicked. Let's quickly do a quick 10 minutes, let's say, background of what, like, how do you do astrophotography or whatever that is called?
I'm the most basic person. I have the most basic understanding of astrophotography of anyone here. So it's like, I was interested in photography for a long time. And then recently, Jan 1st, I with some money which I was able to save and with some money I was able to get from my grandparents, I bought a camera. And then I bought a zoom lens. And then with photography, like I was telling you, it's a very expensive hobby. You start off with a camera and then you buy lenses, and then at a point you see that the lens is more expensive than the camera. It's insane. So astrophotography with the moon, it is fairly simple actually. The level of astrophotography I do it's almost laughable. But it's like I don't have a tripod, but you have your camera, you point it at the moon, and then you take I think for a very high quality HD photo, you have to stack multiple photos of the moon on top of each other. So it's not like one photo looks that good, because with one photo you're not able to capture that much detail. So you stack multiple photos on Photoshop, you edit them, and then the final result comes out, which is much better than any of the single images you clicked. And then you look at it and then you're like, wow, this is nice. So with astrophotography, I'm actually having this long longing to collab with Ad Astra. The thing is, they have a telescope, and then I have a camera. Their lens, it's like my maximum magnification my lens can do is 210 mm. With my camera, it can do 315 mm because it's a crop sensor. So to 315 mm, I think it is at I don't know, 15 times, 20 times zoom. That's it. the lens which Ad Astra has on their telescope, I think the lens they have is 1500 mm.
1500 mm.
Yeah, at that point you can just look at bacteria on the moon. It's that zoomed in. So I mean, with the eyepieces, it goes even more, because 10, 20, 30x eyepiece magnification on top of the 1500 mm lens, it is crazy. You can look at the individual craters on the moon.
Wow.
That high level. But the thing is, I was speaking with the Ad Astra guys. They told that the joint which attaches the camera to the lens of the telescope, that is broken. And they have only a joint for I think Nikon, and they don't have a joint for Sony. And I have a Sony camera, but their Nikon camera, like if you remove the lens on the camera, you cannot take photos. That is a thing which the camera manufacturers decided to do. But in my camera case, that's not true. If I remove the lens also, I can take photos. So that's a long collab in the process of happening someday, hopefully. Because if that happens, I can... like recently for Atmos, Ad Astra showed Jupiter and Saturn with a basic pair of binoculars, 15x zoom. You can see the 4 Galilean moons of Jupiter.
Really?
It is actually insane.
Wow.
It is so insane that with my camera you cannot see that. You can just barely distinguish that is Jupiter, and forget about Saturn. It's just too far away. But with Ad Astra's telescope, you can actually like take multiple photos of Jupiter. You can actually make a 4 or 5 hour time lapse of Jupiter. Like you can, like I've seen this on Reddit and Facebook, where you know the Galilean moons, from our perspective, they complete like half the orbit of Jupiter, and you can actually see that. Like it starts from here and then it goes here, and then in that time Jupiter will also have turned. So the great red spot is here. At the end of the 4-5 hours, the great red spot is here. And then you can also discern the colors. Like you've seen all those beautiful bands, white, orange, red, that you can actually see not like that clearly, but it's actually insane how well you can see. Same with Saturn, you can actually see the rings of Saturn. But again, that is a collab which I hope someday happens before I graduate. But that is something.
We'll try and make it happen.
We will try. And I mean, if you want like basic astrophotography, a tripod is a minimum. Because stability and
so how does the composition work? Like you just put it into Photoshop and you just line up all the edges, or like how do?
See, it's like you have to take burst photos at once, and then you have to, like, this is very difficult to do with handheld camera, because you're zoomed in that high that even slight hand movements will completely shake the image on the sensor completely. It's like the moon is here one time, and then the next image the moon is completely out of frame. So with tripod this works best. So you point it at the moon, and then you take, say for example, 25 photos. And then it's like when you take photos of the moon, you have to make sure that when you start shooting, there should be no already present shake in the camera. So it's the typical thing is that you point it at the moon, you focus it correctly, and then you start a 10-second, like you remove your hands off the camera, and then you start a 10-second timer, so that any vibrations are there, it will just die down, and then it will start taking burst photos, and then you import all those photos on Photoshop, and then Photoshop has this magical feature. Like, it's just black magic in Photoshop. You tell something, it'll do it.
Alright.
It will stack all those photos, and then if you, like, have you seen those images where the dark side of the moon is also seen with the bright side of the moon, and then at the edges there is a white glow, and then there are stars in the background? That is that is a fairly difficult shot to capture, because that is not one single photo. That is a composition of multiple photos, where first you take photo of the night sky with just stars, and then you do the same trick. You compose multiple photos one on top of each other. you get a HD quality image.
Yeah.
You call that background.
Yeah.
Star background.
Yeah.
And then there is one photo of the moon
Yeah.
which is overexposed.
Yeah.
Where it is completely bright. It's
Yeah.
like a white disc.
Yeah.
That is another photo.
That is the background measuring.
That is it's like almost a halo ring
Yeah.
around the moon. That is shot 2. That is done. And now comes your main moon part. Let's say you want to do it with half moon. So you take say 25 photos of half moon. You stack that, and then that is image 3. And then now you go into Photoshop, and then you stack all these 3 layers one on top of each other.
Compose everything.
You compose everything. That, and then if you have crazy lenses which go to 600 mm and all, you can. It's like the moon is here. It is up in front of your face.
Yeah.
That is like I said, those lenses are more expensive than the camera.
Yeah.
So that is pretty insane.
But you can get the Ad Astra one sometime. Like maybe they can.
Sometime,
figure out the
hopefully.
attachment. Yeah, hopefully. Bro, I wanted to talk about so much more. The memes.
The memes.
History as well. Oh, that's.
History, yeah.
I love the math memes that you post. Like it's insanely funny. Thank you so much for posting.
You're like, I've said this to you multiple times. You're like this one fan I have on Instagram. Everyone else is like, okay, what's this guy posting crazy memes again? I don't understand why this guy is so fascinated. And then there's you who balls out every time. It's like, wow. So it's like a crazy dynamic.
No, I love the stuff. Like even the thing you said, like approximating a cow to a square.
Yeah. See that is a standard physicist joke.
Still, like I love all of that
Approximate cow to a sphere, penguin to a cylinder. Yeah. So it's very standard.
Very standard. But yeah, it's just very funny to me. Anyways, I think we'll have to end it now. Thank you so much for making the time. We'll do a part 2 for sure. I have much more stuff to ask and
Hopefully.
for us to discuss. We didn't get into most of the stuff that I wanted to talk about. Chalo. Yeah,
I was very honored that you had me on this podcast.
Hey bro, chill only.